Okay, here's our solution for hard number 1, and this is an example problem for all types of problems that you have two different objects that are racing each other or meeting each other, and you guys have two of those in your problem or in your homework. So this is how you solve them. So you start out 9 meters from the door of a bus. You're behind the bus. It pulls away with an acceleration of 1 meter per second squared, so the bus is increasing in velocity, and you're starting at a constant velocity. Somehow you instantaneously achieve a velocity of 5.7 meters per second without accelerating. So you're going 5.7 meters per second the whole time, and you're trying to catch this bus. And part A asks you how long does it take for you to reach the open door of the bus. Here's your key for these types of problems. When it says you reach it or two objects meet, what it's really saying physically is that their positions are exactly the same at that same point in time. So to start any problem like this, you want to sketch it. And here you are. Okay, you're 9 meters behind the bus. And I'm just going to draw a box for our bus. Okay. And it pulls away. I know my bus has an acceleration of 1 meter per second squared. And to model this problem for all two particle problems, the best way to do it is to come up with, if you can, get an equation for each particle in the problem. So an equation that gives the position of the particle as a function of time. So to do that, we need to define an axis, and I'm going to say that this direction is the positive x direction, and my origin is going to be right where this person starts. So he's at a position of 0. To write my equations for the person, I'll do it in two different colors here. For me, I'm going to call that my equation, let's do this. We'll call that x of m for me, position of me, at any point in time is equal to, I'm using this equation, my final position equals my initial position, plus my velocity times time, plus 1/2 acceleration times time squared. And this will give me my final position at any point in time after t equals 0, if you plug in your time. So if we plug this in, my initial position for the guy is 0 meters. So this value is 0. I'm not going to put anything in there. My velocity to start is 5.7 meters per second. And this will be times time. And then I have no acceleration for running. I stay at this constant velocity, so this term is 0. So I have a simple equation right here for me as a position of time. For the bus as a position of time, we'll call that xb, position of the bus at any given time, can be found by, well, its initial position is not 0. It's starting at, if this is my origin right here, my bus is going to be at 9 meters. And I add to that its velocity. Well, its initial velocity is 0. So this term for the bus is 0. But it does have an acceleration. So we're 9 plus 1/2. My acceleration of my bus from my problem is 1 meter per second squared. So times 1 meter per second squared. And times time squared. I'm going to write both these equations without any units so we can do some math here. This is 5.7 times t. And my equation for my bus is 9 plus 1/2 times 1 is just 1/2. So 1/2 t squared. Okay. So to answer part A, how long does it take for you to reach? Remember, reach is when my positions are equal, the door of the bus. How do I do that? I set x of me, my position function, equal to the position of the bus at any given time, and I solve for time. So this will be 5.7 times t. This is equal to 9 plus 1/2 t squared. And if you solve for t here, t equals 1.89 seconds. And you get two answers here. T equals 9.51 seconds. Okay. Why are there two answers? Let's look at that graphically, and that'll help you see what's going on here. So if I pull up a graph of it, I've already defined in my calculator. I called function b. Just a side note, your calculator doesn't like to graph t, so I substituted it as x. So this is my function for my bus. Bus as a function of time, x represents my time here. And this is my function for me, it's a function of time. And I'm going to graph both of those. So my first one, I'll graph my bus. And there's my bus, it's outside of my range. And my second one, I'll graph me. And let's adjust my axes. I think we go up to 75, does it? And let me change this to 10. 15. So here's what's happening. My bus is my blue line, it's accelerating, starts out at 0. My slope right here of my position versus time graph is 0, so I have a velocity of 0. My bus slowly starts accelerating, so it's speeding up, and the curve should increase in slope, which means my velocity is increasing. I'm running at a constant velocity, I start at the same time. That constant velocity gives me a nice straight line right there. So what happens is when I first meet the bus, this first instant in time, which is my 1.89 seconds, I'm going faster than the bus. So I'm passing the bus. I'm at the same position at split second time. I pass the bus. The bus continues to speed up. I'm going the same speed. Eventually the bus is going to pass me, and that's my second point in time. So to answer the first question, how long does it take for the reach open door? Well, the closest time, or the earliest time that you could, is 1.89 seconds. Okay? To answer the second part, you do have a second opportunity if you miss the first opportunity. You can hop on the bus at 9.5 seconds. Part B asks, what's the maximum time you can wait before starting to run and still catch the bus? To answer this question, one of the best ways to look at it is graphically. If I can only reach the bus at one point in time, that means that my line only intersects my bus position versus time graph in one point. Okay? If it intersects it in 2 points, that means I could have waited a little bit longer, because that means I'm going faster than the bus when we pass the first time, and I'm going to meet the bus again. So what does that mean graphically when both of these meet at the exact same point? That means my line graph is tangent to my bus position versus time graph, and in other words, their velocities, or their slopes, are the exact same at the point in which they meet. What does that mean physically? If you think about it, I'm running at 5.7 meters per second. If the bus is going faster than me, 5.8 meters per second, there's no way I'll ever catch it. So the last point in time that I can still catch the bus is when the bus is going the same velocity as me. And that means that my graph is tangent, and they're equal to each other. So, how do I calculate that? Let me show you how to do that. So to find the point in time where the bus and I are going the same speed, I'll go back to my position versus time graphs. How fast am I going? Well, I'm going 5.7 meters per second the whole time. So I need to find the point in time when the bus is also going 5.7 meters per second. How do I do that? Well, I'll just do a little calculus here. We'll take the derivative of this function to get my velocity function. So my velocity function is equal to, well, the derivative of 9 is 0, so this drops out. And if I take the derivative of this function, 2 times 1/2 is just 1. So my derivative for my position versus time function for my bus is my velocity versus time function for my bus, and it's just t. What does that mean? That means to figure out when v of t equals 5.7, well, I just set this equal to 5.7. So t equals 5.7 meters per second. When does that happen? Well, that happens when t equals 5.7 seconds. In other words, the bus is going 5.7 meters per second at time 5.7 seconds. Now, is that when I start running? Well, if I wait until the bus is going, the bus is going to continue to move. If this is my bus moving. If I wait until the bus gets to be 5.7 meters per second for velocity, and I start running at 5.7 meters per second, there's no way I'm going to catch the bus. I need to be at the bus at the moment in time when the bus is going 5.7 meters per second. And that's at t equals 5 seconds. So how do I know when I can run? How long do I wait? Well, I'm going to figure out how far the bus has traveled in that amount of time. Because I need to be at that same position that the bus is at time 5.7 seconds. So I'm going to plug that into my x for my bus equation. So this is where my bus is at 5.7 seconds. Well, my bus is at 9 plus 1/2, 5.7 squared. And this comes out to 25.245 meters. So what does this mean? At 5.7 seconds, my bus is traveling 5.7 meters per second. The same velocity that I'm traveling. Okay. Where's the bus at? The bus is 25.245 meters. So at this point in time that I care about meeting the bus, we'll call it this time right here, this distance is 25.245 meters. What does that mean? That means I need to travel 25.245 meters to meet the bus at this point in time in 5.7 seconds. Can I do that? Yes, I can. How do I figure out how long I wait to do that? Well, I'm going to figure out how long it takes me to travel my 25.245 meters. So how do we figure that out? I'm traveling 5.7 meters per second. I'll go back down to the bottom. I want to travel 25.245 meters. This is my x of me equation, equals, and that equals 5.7 times my time. We'll figure out how long that takes. So t equals, we get 4.429 seconds here. And that's how long it takes me to travel the same distance. Well, how long does it take the bus to travel that far? It takes the bus 5.7 seconds. So how long do I wait? Well, the bus needs to travel for 5.7 seconds. I need to wait a little bit so I can get 4.29 seconds of travel time. And if you calculate this without rounding, we get 1.27 seconds. In other words, I wait for 1.27 seconds. The bus has already traveled for 1.27 seconds. I start running. So now I've traveled for this long when the bus has traveled for 5.7 seconds. That puts us both at the exact same position because I've traveled for this distance. The bus has also traveled for that distance right here, and we're at the same point in time, and that's my answer. I can wait 1.27 seconds. If I wait any longer, the bus is going faster than I am before I catch it, and I'll never catch it after that point. So that's how you solve the problem.